Okay, so now the next to last is an overview of a slicer, 3D slicer with some background. So 3D slicer is a technology delivery platform, both aimed at end users, which are not programmers, as well as at developers, which are programmers. And and you'll see it later in some of the slides. It's an entire ecosystem. So it's not a monolithic application, but it's multiple layers of libraries and toolkits, and then applications and extensions that leverage that infrastructure. So sometimes people ask me, why should I use 3D Slicer? And one important aspect that is not very obvious, but I think very important, is longevity. We have been around for a long time, and there is no indication that this will stop. And I think that's important because if you develop on a platform, you want to have reasonable confidence that the platform will be up to date and available in a few years down the road. Slicer is free, it's open source. We are using a license that is very liberal, no give back requirement, which means it's also friendly for commercial use because companies can use it without asking for permission, without having to pay license fees. There is a rich set of features, basic visualization, image analysis, interfaces to devices, and those were created by different communities. So it's very broad and in some of the core aspects very robust. Of course, the closer you get to the bleeding edge of technology, the less robust it is. So there are areas that are very robust, and there are areas where you have to be careful. And today, while it started more than 25 years ago as a master's thesis, today it's supported by an international community that is interdisciplinary, both in the core aspects as well as in the application aspects. And one of the vehicles, and it was mentioned by Juan, and the fact that we do it here in the Canary Islands would not happen without Juan and his group, is the project week, where people come together to work on the project and interact with other developers and with some of the core developers. Slicer is intended for research, not for clinical use, and it is focusing on subject-specific work. So if you want to run pipelines to do cohort comparisons, there are other tools. Or you could use some of the elements of the Slicer platform. But if you want to analyze the data for surgery tomorrow, then Slicer is your way to go. And what you see here is from the 90s, where we had an open bore interventional MRI scanner with a display showing 3D Slicer. And you see one of the neurosurgeons holding a track device. So we have been doing this kind of business for a long time. When we deal with patients as opposed to healthy subjects, we deal with pathology. You have tumors, you have infarcts, you have all kinds of pathology which distort normal anatomy. And those distortions are important to capture and understand in planning and executing treatment of the patients. And here, just as an example, on the left side, you see a brain tumor in green. You see some of the white matter tracts extracted with tractography of the corpus callosum, and in blue you see the ventricles for reference. If you look at this U-shaped structure that are some of the corpus callosum fibers, you see that the part close to the tumor is yellowish instead of green like it's on the other side. And this is because the colorization that you see here is the fractional anisotropy, and the tumor has basically modified FA in the peritumoral edema region. What you see on the right side, same tumor. Now it's not the corpus callosum, but you still have in blue the ventricles for reference. I put the seed into the internal capsule, which is at the bottom, the red sphere at the bottom. And you see some of those fibers going up to the annotation that is labeled hand motor area. And what you notice is that the tumor has pushed those fibers not towards the ventricle and the midline, which is what I would have predicted, but has pushed them to the back. And this is, of course, critical information if you want to do surgery and tumor resection. It's important to know where is the corticospinal tract. So these are just examples of what you can do. I haven't talked about how you can do it. And in particular for tractography, Zora will tell you more about that aspect. Sorry. So again, subject-specific analysis and annotation. So you need algorithms that allow you to do it quickly. And over the years, I got tired to repeat the same story every time a new student came on. And so what I did is I put it on one of our wikis, and a little bit megalomaniac called it Ron's Rules for Tools. It basically says, be careful how many parameters you put into your algorithm. And I don't believe you that the algorithm works until it works on my computer with my data. That one is actually a very big thing when you deal with students, because getting the algorithm to a stability that it will run in someone else's environment is non-trivial. And then, of course, if you want to do interactive work, we have to be fast. You don't want to be slow. And don't do parameters. And that's not, again, that's not my insight. John von Neumann, who is one of the founders of computer science, apparently said this in the early 50s, that with 4 parameters, you can fit he can fit an elephant, and with the 5th, he can wiggle the trunk. And a group of mathematicians actually published a paper in 2010 where they actually provided the formula. And I actually yesterday found the paper in X-Archive, somebody presenting an approach where a single parameter can do the elephant. But I have to admit, I haven't understood the mathematics yet, so I'll need some help there. So, few years, so we have been at it for a long time, a lot of algorithms, software infrastructure, and then artificial intelligence came to the forefront. AI has been around since the mid-40s, but we didn't have the hardware to do AI for real. there was an attempt in the 90s when the first generations of supercomputers became available. And at that time, people were experimenting with one hidden layer in the ANNs. And one hidden layer, turns out, is not better than just doing statistical classification. So people gave up on it. Fast forward today, the discovery that GPUs can be used to do massive amounts of computations of the kind that's needed for AI has revolutionized the field. So in the last decade, we've seen people taking up AI again and moving to ANNs, artificial neural networks, with more and more hidden layers. For example, ChatGPT has over 100 hidden layers, and ChatGPT-4 is more like 120 layers. About 10 years ago, one of the first applications of this technology was in computer vision, and it was enabled by a database with 14 million hand-labeled images. So those were 2D images, like what you see in the little inset and here. And each had a label like dog, cat, badger. And then you trained your ANN with this, and then you fed it a new image that was not in the training set, and it told you this is a dog. This was made possible by the availability of this ImageNet. We don't have something like this in medical imaging because it's much more difficult to gather medical image data because virtually everywhere patient confidentiality is protected by law. And while this is an important thing to protect the patient's identity and features, it also is a big hurdle for us to do this type of research. So people got in the medical field, and in particular in radiology, people got very excited, and about 4 or 5 years ago, there was this excitement, peak of inflated expectations, where one of the mathematicians that were in the field said, stop training radiologists, our algorithms will take care of diagnosis. Turns out that that call was a little bit premature. There were about 2 years ago, I did a review. There were about 100 FDA and CE marked products that use AI technologies that were available on both sides of the Atlantic. And virtually none of them were usable. And so this led to the thrust of disillusionment, and we are slowly climbing out of that hole. Where are we today in our field? I'm giving you 2 examples. One comes out of the Martino Center, the group around FreeSurfer, basically took results of FreeSurfer segmentation and used the labels to train a network and combined it with a trained network to perform interpolation. And this allows you to synthetically create, let's say, proton density weighted images out of a T1 weighted image. And in contrast to FreeSurfer, which takes several hours to run, this algorithm will do the inference on your laptop in a few minutes. So one of the advantages of trained networks done right is that you can accelerate the processing. What you see on the right side is NNUNet, and NNUNet is an attempt to automate the parameter setting for the ANN. And as you see, it's a very complex internal organization. The algorithmic work was done by the group at DKFZ, led by Klaus Meyer-Hein. And the first author of this work is Fabian Isensee. This was published a few years ago, 2021. Another postdoc took that torso CT data, manually labeled and semi-automatically labeled using a bootstrapping approach. Using this approach, there is now another algorithm that is called total body segmentator, which is integrated into Slicer and allows you to basically feed it your torso CT scan or chest CT scan, and it will do the labeling automatically and reasonably well. Not perfect, but impressive. In order to do this kind of work, you have to have the data and you have to organize the data. It turns out that data scientists working in the field spend most of the time on data aggregation, data cleansing, and data labeling. So the actual algorithmic work is only a very small part. And so NIH, and in particular NCI, decided to develop an environment to facilitate this work. And so you want to have data that is openly accessible, that is organized in such a way that you can read the data, search for particular features so that you can build cohorts. And the data should be interoperable, so if you have different collections, there should be a way to use them together. And finally, it should be reusable. So I published with it. You want to duplicate my results, you can find the data and publish with, and rerun my algorithms as a quality check, or rerun your better algorithm to beat me. And so these are the FAIR principles, and they have been propagated for a while, but they have only been recently implemented in usable ways. And there are efforts both in Europe and in the US. And the one that I'm involved is the Imaging Data Commons, which is funded by the National Cancer Institute in the US, and it is an entirely cloud-based resource. And if you work in the cloud, you need to rethink the way you are working. All the data and the tools are in the cloud. That's the most efficient way of doing it, as opposed to the traditional way where you have somewhere a server with the data, then you download it to your machine to do the analysis. People, when they hear cloud, they have heard horror stories. A student forgot to turn off the VM, and it costs $20,000. And those are true. So you have to be very careful about what you're doing. And you have to train your people accordingly. However, if you do it right, and this is an experiment that one of Andrei Fedorov's people Vamsi and postdoc Deepa have done on the topic. They ran the total body segmentator on 120 plus thousand CT scans on a cloud resource. And the cost, and this was of course optimized. This was not one guy woke up one day and said, let's do it today. There was a lot of careful engineering involved to do this, but it took a little bit over 8 hours, and the cost was in the range of about $800 to 120, the segmentation of 120,000 CT scans. So you can get it down to cost factors that are very competitive compared to everything else, if you know what you're doing. Now, okay, so we have a first generation of usable algorithms out of that technology. We are at the beginning, not at the end. Things are not perfect, but they are not bad either. So here is one example. Steve Piper, who has been part of the team for a long time, took SynSep and the trained network that came out of the BRADS competition at MICAI, which is a long-standing competition to do analysis of brain tumors from MRI. He combined the two and ran them on patient data sets. So what you see here is basically very obviously in yellow, this is the brain tumor. You see the segmentation into gray matter, white matter, ventricles, deep gray matter. You see, for instance, the thalamus has been pushed forward by the tumor. In this example, thalamus being labeled in reddish color here. So this is the kind of work that we can do, and this runs in a few minutes on a laptop once you have everything set up. That's, of course, will take a long time to set everything up properly, but when you're ready to go, you can do it reasonably quick and quicker than any other method. And again, we are at the beginning, not at the end. So these are the first examples of what can be done. Nikos asked me to mention TMS. There is some TMS working. I explained it to you two guys yesterday, so I'll go relatively quickly over it. So the work that was done was a combination of some people at the PNL, SPL, and then a computer scientist at Boston University in Daniel Hand's group. And what we see here that they ran a simulation of the magnetic field on the brain. And I'm going quick, first of all, because I'm running out of time, and second of all, because I really don't know a lot about the details. But what can be done, so again, here you see the setting. This is Lipong head being tracked. This is the TMS coil being tracked. And then you can basically run the simulation with the information on the data. And you can interactively move the coil in the simulation, as you see up here, and everything gets updated very quickly. And once you have everything set up, if you did the MRI acquisition, you can use this to actually, and that's what you see on the right side of the image, the tractography is being updated based on the focal spot from the TMS coil. And you see in the lower left, if you want to take a picture for the references. Good. So a little bit more about 3D Slicer, very quick. Again, mid-90s is when it all started. And now we have almost 1.5 million downloads for the executable. And we don't have a good way to figure out how many checkouts we have on GitHub. But probably a lot, but I don't know. We have the slicer core, and then we have extensions that are configured to self-install. And we have currently about 170 extensions. The community of developers communicates through a forum on one hand, and on the other hand, through twice a year in-person meetings. These project weeks that were mentioned. It's being used a lot. Just 2023, if you look for the keyword 3D Slicer, you'll find over 1,300 papers quoting the software. And so, and again, 3D Slicer is a stack of libraries and toolkits. And what you see here, this slide I got actually from Gabor. And the point is that 99% of the code is already there. So if you want to do an extension, you just have to do the small part that is not there. Everything else you get for free. And here are some examples of very recent extensions. So this is 6 extensions were submitted since June 2023. We don't control who downloads the code, but we have a quality assurance process for uploading new extensions, because we want to make sure that people don't insert malicious software and so on. So we only accept extensions that are open source and where we can inspect the source code. The forum, which is the electronic way of communicating with posting questions and answers, has seen a lot of traffic, and as you can see, the curve is pointing upwards in a nice way. Project week, I'll skip, and this is also an important slide. It basically tells you that it's not a single guy sitting at home doing Slicer, but it's really a community of developers. So these are not extension developers. These are contributors to the Slicer core, just since last June. So 38 contributors, 12 of them first timers. And I think that this is where I will stop, given the time that we are on, and I'm open for questions.
Any questions?
Thank you. Thank you for a wonderful presentation. So I got two questions. One is I'd like to maybe probe your opinion, because when you were describing this local versus cloud infrastructure topology, I have sincere doubts that might work, and I inspire or I base my insight in the gaming industry. So the gaming industry um, has tried to have local cloud-based infrastructure, but due to this lag, the latency in the network, have avoided. And now what they tend to do is you have cloud distributed methods or a code that you executed locally. Although it's cloud distributed, the most important infrastructure is this Steam, which is now owned by Microsoft, which is a great success, right? So this is my understanding, and the reason I'm asking you is, so what is it that I'm not understanding? Maybe would you explain your option for the cloud? One thing is that this slicer, one of the main things that I love about it is this insight, this instant insight you get about your tinkering with the data. And if you add this time lag, wouldn't you lose that? That's why I'm asking.
Yeah. So basically, I have to ask you the other way around. What is considered real time? There is no definition of real time. If you look, if you go back like 40 years, real time was 30 frames a second. In the gaming industry, in gaming, semi-professional gamers, if you don't give them 60 hertz, they complain. In the context of surgery, you can get away with 15 frames per second. So it depends on the application context, what real-time really means. That you have to keep in mind. So if you have a tracking system intraoperatively and you're moving something around, what you want is two things, fast updates and low lag. Those are two different things. The reason, for instance, that head-mounted displays have become practical, they've been around for 30 years. I've had a head-mounted display on in the late 80s when I visited the lab. And if you go back, the first not head-mounted display, but AR display, augmented reality, were experiments by Sutherland, who at that time was at MIT, and that was in the 60s. They had basically a boom-mounted camera with a handle, and they had the transducers in the joints of the boom. And because it was an analog setting, they had very low latency, and latency was the killer, not the refresh rate. So you have to think about both these aspects. So if you want low latency, high refresh, then any network, forget it. By design, Ethernet doesn't have you guaranteed return times. So because it is designed to be resilient and a network, so if one connection breaks, the network routes in a different way. That's why you don't get necessarily guaranteed times. So for this type of work, you have to be local. Everything else where you don't have this requirement, and I consider interactive segmentation in that second class. The latency introduced by connecting to a cloud resource is acceptable and workable. Sorry, it's a little bit.
I was following and I understand. The only but I can put to that is, so I was reading this feasibility poster from a few months back, addressing the issue of why is fMRI not used typically as we were all hoping. And one of the reasons is because it's difficult to process the data while the subject is in the scanner. So maybe a little but is, okay, but why do you need to upload a significant amount of data? Your data is local, but your processing happens in the cloud, and you need to push the data there.
Yeah, and why? Because the vendors are cheap. The vendors put the minimum amount of hardware into the devices. If you can save thousands in hardware on the 6,000 scanners, that's $6 million that you saved. So traditionally, what the vendors have done, not just on MRIs, but on other things, is to use as little hardware as possible and optimize by putting more software engineering effort in the post-processing, taking advantage of everything that we could. Because if it costs you more to do the software engineering, but this is a one-time cost that again spreads out. So if you invest $3 million in software engineering to save $1,000 on hardware, you have on the balance sheet $3 million profit.
In the short term.
Yeah.
Hardware is extremely due to upgrades. Software is a button press. On hardware, you gotta go out to every single machine, take them down. That's $10,000 easily to take down an MRI, probably more. So,
yeah,
cheaper hardware.
So I think in the interest of time, I don't want to torture Zara much more.
So, in the last of the day, Professor Zara will talk to us about the usually when we talk about. So.
Hello, everybody. I am getting here. How do I share? Oh, this area? Okay.
And now you say,
Hello.
Press that. Up at the up arrow.
Yes.
Toolbar.
Allow, why won't it allow?
It did before,
It did before. Could you try again?
so not
Yes,
allow,
now-
or what you,
now-
how do I
let's
close
just
it?
press not now, for now.
Okay.
Okay,
Okay.
and then let's try again. Oh, just missed that one. This one, yes. Could you try to select a different option? Okay, read only that one.
The entire screen?
Or
No.
maybe this Sunday program. I believe that is your.
No, this is this one.
Ah. So, okay, maybe we have to opt for entire screen.
yeah, that's what I would do.
And now you just select your presentation, whatever.
Go to presentation. Perfect.
Okay.
Yeah, no, it understands. No, it has to be. Oh, okay.
It works.
Is it okay?
Yes.
All right. So I will be presenting on the MRI tractography using 3D slicer. And so what I'm really going to speak is about the neuroimaging tool in 3D Slicer. I am a user. I'm a very naive user. My background is biology. I have no knowledge in mathematics, physics, programming, nothing of all this that you guys have. I am using this software and somehow I need to feel comfortable with it. And I think this is very important in all in translational research. When you work with human subject, with clinicians, the clinician need to be able to use the software and trust it, and feel familiar with it. So I am going to present it from my perspective. I will present first what background I have. What do I need to know or accept in order to do DTI, diffusion tensor imaging? And so the background is probably sounds kind of a little bit funny for you, but this is a mean how to make the user familiar with the whole process and with the using the slicer. And then in my second part, I will present a few examples of what I'm using 3D Slicer for in terms of projects. And it's mostly projects, so it's a neuroimaging, and these are projects in mental health. So, okay. So I think the one of the issues is we have this diffusion weighted image, which is extremely blurry. You see my other cursor is very tiny. So on the image on the left, you see the gray matter is white, and the white matter is dark, rather dark, and you really can't see much in it, right? When you move over to the image in the middle, it kind of starts taking some form for me. So once the diffusion tensor are being, so once the image has been processed and the diffusion tensor has been calculated and the fractional anisotropy map has been done, it starts looking nice, especially when there is color by orientation added to it. It's then we can read that some of the tracks that are in blue, they go up and down, those in green go back and forth, and those that are in red goes right and left. That starts looking like, okay, this is some white matter in this brain. And then the last step is to use FA or fractional anisotropy to reconstruct these fiber tracks of the whole brain. And so maybe I need to go. I need to be familiar with some of the background. And so I think the very important thing for people with my background is first to figure out that the diffusion magnetic resonance imaging is the same as DMRI or diffusion tensor imaging or DTI. One has to be aware of it that what we are measuring is just diffusion of water. And as you all know, the water diffuses differently if it's in a space that is not constricted. So for instance, in the cerebrospinal fluid, the water molecules will diffuse in all directions. We have diffusion in all directions. In areas of the fiber tract, the diffusion of the molecule is restricted in the direction of the major fiber tract, and that can be assessed with this very cool thing, which is called diffusion tensor. Again, I have no clue what the diffusion tensor is, but to see these ellipsoids on here. That gives me some idea what it might be, right? And that also helps me to understand the DMRI measures. So maybe let's start with the one that's the easiest to understand. This is the axial diffusivity. This is the vector lambda 1 in the long direction, in the longest direction of this ellipsoid, of this diffusion tensor. Radial diffusivity tells me how fat it is, so it's lambda 2 plus lambda 3 divided by 2. And then it's a measure how big the ellipsoid, the ellipsoid or the tensor is, and this is measured by mean diffusivity, which is lambda 1 plus lambda 2 plus lambda 3, and that gets divided by 3. The most important measure is the fractional anisotropy. That's quite complex. Okay. I accept it as it is, and that's fine with me. So what do I need to understand to generate, to understand tractography? Well, we start on the right. In each of the voxels, this is represented here by square on the left. The diffusion tensor is being calculated, and it has a major direction, and that's defined by the arrow. And so in voxel 1, all the way on the top on the left, this tensor just goes to the next voxel, and it goes to next. Okay. If you start seeding, and you kind of run different paths. So what does it translate to on the image on the right? There's an image of the brain where each voxel has this tensor calculated. It has, if you can see it even better, there's a shape, and there's also direction to it because it's a 3-dimensional. And most important, the track that we ran from the voxel number 1, that's represented by the tractography in red, and this is the corpus callosum. On the other side, the track that has been reconstructed from voxel 2, this is the one in blue, and this is the corticospinal tract. So one really needs to, and I would like to, one needs to remember that this is just diffusion. So streamlines are not axons, but mathematical constructs. And you cannot repeat it often enough with people that do not have a background in all that what you guys are doing. And so, what is the process in the 3D slicer? How do I do tractography? How do I reconstruct these tracts? And so this is an image on the left. There is an image of the corpus callosum. You can see it kind of in white. In the middle, the region of interest has been drawn over the corpus callosum. And in the third step, you just see tracks from this region of interest using 3D slicer platform. And usually when people do that, the first time it's like, wow, it is amazing. It is pretty. 3D slicer is amazing on doing the reconstruction of fiber tract using single tensor. But it's not, I think there can be done more. by using a two-tensor tractography. So when you, for instance, the image that Ron has shown, when you have this TMS device and move it around, this in the 3D slicer, you can easily reconstruct the fiber track using one tensor tractography. When you move forward to two tensor tractography, it's more it's more computation intense, in that really cannot be done on the spot. We do like the two tensor tractography because, as you can see between the two pictures, left and right, on the right side, the two tensor tractography really detects many more streamlines. And it detects many more streamlines because the limitation of single tensor tractography is in area when the tracks are fanning out or when they are crossing. So if there's a crossing within the same voxel, if there are two tracks crossing within the same voxel, the tensor stops. Okay. However, in the two tensor tractography, where there's not just one arrow in voxel 1, but two arrows in areas of fanning or in areas of when two tracks cross, the tractography can go in two directions. Okay. The two tensor tractography that we use is called UKF, or Unsent-Kalman filters, that has been developed by Yogesh Rathi at PNL and has been published by Malcolm in 2010. So if the tractography doesn't need to be done right away, but if we are interested in more tracks, we do this more advanced method. This method is also automated. So if there are many more images, it really makes sense to pre-process the data. So what we do, we do the whole brain tractography using two tensor tractography. Then we also need region of interest. So instead of drawing region of interest manually, as what I shown before, free surfer parcellation can be used, and free surfer is very quick these days to generate about 70 of this region of interest in the cortical area and subcortical area. It also generates white matter parcellations. So the result, so when we then select streamlines, so we load up both of these images and then we select streamlines of interest. And we either can do it manually again, which is really good in the beginning of a project, when you kind of explore what, how this track should look like, or it has been also done in an automated approach when you have many more images to process, because the manual part is somehow short. The manual part takes a lot of time. And so this is, for instance, here is on the right, as an example, this is the superior longitudinal fiber track plus the arcuate fasciculus. And it is a pretty nice reconstruction. Here I'm showing the same thing. In the middle is the superior longitudinal fasciculus. There are 3 of them in different shades of green that you can see in the middle. In the arcuate fasciculus in yellow, and then on the right-hand side, I also put the corpus callosum in it, and you see then with two tensor tractography days, those tracks really, you can see that they've been tracks that intersect. And just because it's so pretty, I also put all these, the corpus callosum and the superior longitudinal fasciculus in the entire whole brain tractography, which is on the right. The tracks that can be extracted. There are a bunch of them. I don't know whether I should read through all of them, but for instance, using this automated method to reconstruct these tracks is called white matter query language, which has been done also in our lab by Damien Wasserman and Nikos Makris. And so they do end up with about 11 association tracks, 8 projection tracks, and 7 commissional tracks. So this is pretty nice selection of tracks. So what do we do with it? So another feature of 3D Slicer is that you don't only visualize the tracks, but you can quantify it. You can extract the MRI measures. And this goes into the microstructure, so we can learn something about the microstructure of the fiber tracks. And we will be learning even more when we have Magnus data from Carl Frederick. So to learn more about the fiber track, about the bunch of the streamlines, when you look at the fiber track, people always think like, oh, let's look into the number of streamlines. That's going to give us some information. That actually hasn't turned out to be so informative for us, for people that work in mental health. It is the fractional anisotropy who is more interesting in some of the other measures like radial diffusivity and axial diffusivity. So we are calculating the mean of the fractional anisotropy over the track. And so, for instance, in this example that I have here, we can use it to compare the brain white matter of people that are healthy and people that have schizophrenia. And in this example, the sample in blue are healthy people, and when you look, when you compare the red dots, these are results from people with schizophrenia. And again, this is, so what we compare here and what we see differences is in FA, and this is for the SLF, superior longitudinal fasciculus 1, no, sorry, so superior longitudinal fasciculus 2 on the right-hand side, on the left-hand side, and then SLF3 on the left and right-hand side. There are many more, I just picked out something. And this is also extremely small study. So these days we do studies with much bigger data sets, and that's why we need to have things automated. Another example of quantification is this study. So we have extracted a fiber track, and we wanted to know whether this fiber track is involved in pain sensitivity. So this is a study on participants that had been inflicted pain by heating up part of their body, by getting hot patches, and they had to report how painful it was. And here, what you see on the right is that the FA and the radial diffusivity of this particular track correlates with the pain intensity, with the rating of the pain intensity. So for us, what we interpret is that this track really is involved in sensing or transmitting the pain. And because we do see changes in FA and RD, we kind of hypothesize that people with a higher degree of myelination of the tract can experience less pain. So changes in FA when it goes down and RD if it goes down, that might represent myelination. And this is something this is something biological that people like to read from the data. But again, one has to be very cautious. This is just diffusion. This is nothing. This really doesn't describe the characteristics of the fiber, and especially with reviewers, it's very difficult to not to over interpret the data. So what are we interested in today? So these days we are also looking into white matter that goes all the way to the brainstem. This has been made possible by a publication by Nikos Makris. He explored the brainstem with a very high resolution of 50 microns, and he was able to characterize the nuclei. So the issue with brainstem and tractography are two problems, is that all the tracks are parallel and next to each other, and they can be characterized by from which nuclei they start, but these nuclei are usually not, we cannot really see them. And most people even do not have enough neuroanatomical knowledge to be able to localize them. But Nikos, luckily we have Nikos, and Nikos has this knowledge. And so we are now looking into these fiber tracks, and this is important because the brainstem might be central to impairment of cognition and affective and clinical features. And so there are a bunch of diseases that they have symptoms from autonomic system. This like schizophrenia, long COVID, anorexia, and many more. And so this is something that we've been kind of starting to do now. So this is, I'm closing. So this is, we were able to do this work because of the 3D slicer. And so what I've talked about is just the neuroimaging, the MRI module, but the 3D slicer. So this is the website of the 3D slicer, and there's a link to download documentation training. There's also a lot of really good tutorials, and that what it makes it user-friendly. There's also a link in red for the developers. And do I need to mention that there are stable releases and daily releases, and it runs on Windows, Mac, and on Linux. That's it.
Thank you so much, Zora, for this very important presentation, because this tells to every user of Slicer how extremely difficult analysis can be done, and very carefully. So are there questions for Ines?
I have one. So thanks very much. Really nice. And one basic question, like, what is a good nice there. What is a good? What would be a good approach, for example, with DTI to study the connectivity between two regions? For example, if I want to know the connectivity within M1 to SMA, for example, and I want to, okay, this part of the primary motor cortex seems to have stronger connectivity, anatomical connectivity or relation to SMA, for example. How would I do that?
So,
sorry, quantitatively.
Sorry, quantitatively.
Yeah.
So I think
Would you mute yourself?
just talk. Um, I think this is will be kind of a planning. So before you do, so you do the TMS, right? I think it would be very useful for you to have a planning stage. And in this planning stage, I think it would be useful to get this whole brain tractography using 2 tensors of the patient. I would recommend also to have resource, and then you cover by hand. So manually, you see what flags will come up.
Okay. But there doesn't seem to be a quantitative element that is like immediate tell you like, okay, this is an indication or not.
Yes, and so I think as a next step, you use the tool to extract the MRI images like FA, radial diffusivity with AD. At the moment, it probably doesn't tell you much, but when you have several, when you deal with several subjects, I think there might be a pattern appearing for people that are responders and non-responders. So, we mostly do group analysis. You have just single subject. I think what I would be looking for is whether the A and probably the RD, whether the values of the patient are the same to the healthy control. I mean, statistically, it's really, really difficult to do, but it's why you at some point you will need more people. But I don't know exactly what TMS does, but I would actually think that a patient who has really good and strong connections already might respond better. So I don't know about TMS, but there is a study on people that have a depression, MDD, major depression disorders. They get treated with antidepressive drugs. So one of the most common is SSRIs, selective serotonin inhibitor reuptake drugs. So one of them is Prozac, that's known. This one group that actually find out that people that have high FA to start with, they respond better. So I kind of, with the SSRIs, I think what you really change is the transmitter on the synapses. So if the track is well built, it's not degenerated or so. You really play around with the synapses, on the synapses, but you need the good track. In patients that, for instance, have maybe the demyelination, maybe the demyelination is not good, maybe there's some degenerative process going on, or maybe there are less tracks. So the AD might show something like this, but you just have to be really, really cautious with this interpretation. But you don't have to really interpret, you just have to measure it and compare between several subjects. So at some point you might find out that probably people with a good FA will respond better. Or maybe not. Maybe if you treat people with TMS over a certain time, I don't know, maybe there is something going on with the lineage. So maybe these values will be changing slightly. Okay.
Thank you.
So, in the interest of time, we're already a little bit past schedule. I would think we should refer first questions to launch. And I think Nikos wanted to say a few words.
Thank you. Ron, that's wonderful. So, yeah, I would like just to wrap up some closing remarks of the conference. And first of all, I wanted to point out the motivations. You have to put me up the. Excuse me, I'm sorry. Okay. It doesn't. Okay. So I wanted just to let everybody know, especially the local people here, that this was an effort that started several years ago. Ron Kikinis put me in contact with Juan Alzola 10 years ago. And this was the first collaboration. By being involved with Juan's work, I realized the local necessities of the universities and the motivations. There are two big universities, the University of La Laguna here in Tenerife, and the University of Las Palmas Gran Canaria across the channel. So there are two very closely related islands in the Canaries and two big universities, both have medical schools. And here in La Laguna, also the Institute of Neuroscience. So basically, started thinking about collaborating. Ron and collaborating already. So one introduced me to Jose Luis Mora, the physiologist and the imager here at La Laguna, and from there started everything. 3 years ago, Ron and I, together with Stefan, we thought to launch the course, the lectures. And there were clear motivation for why we do that. It's not something that we just come and teach people like a professor. First, we don't ask money from anybody. It's more important to just give recordings, as we do in a very small group of people, but experts in their fields, in what they are saying, and that we like to work together. So it's more a think tank, thinking about projects, thinking about how to do good. As Ron was saying, we do tourism, we do science, to do something good also to society. So basically, we come from Europe, and we work in the United States, like Ron and me. How can we bring something to our countries? I tried in Greece, I tried in Italy, where I studied. All my 16 years I was studying and working in Italy. I became a psychiatrist there. But the mentality is such that they are extremely reluctant of really getting in new people, new blood. And it's not just because the local academicians do not work, it's the system. In Northern Europe, it's not like that. It's like the United States, the Anglo-Saxon system. So can you do an educational reform? Of course you can do an education, but it takes decades, it can take centuries, it can never happen. So these are very difficult societal changes, and the most difficult thing is how to change culture. So culture is the most profound and underlying force. And this is what Juan, for example, is seeing here, is experiencing in changing the mentality, how the perception of companies and the private, let's say, motivation and action should be integrated in the social work and in the system of academics in the Mediterranean area. This is huge, the most difficult thing to do, because it's a cultural issue. It's the perception of people, and they see it as fear. So basically, things like that, we think that should change. And this is a forum for these things with people that have worked in both in both domains, like Risto, who is from Finland, and Juan is now here and is experiencing this thing. So there can be cross-fertilization. Another extremely important thing is to put projects for funding here in Europe and the United States involving people. And this happened for the first time a few days ago, and this was done because of Zora Kikinis, that was able to put a grant on COVID-19 with this anatomy that you saw, that was initiated here in the anatomy department at ULL, University of La Laguna. Last year, Ron told me, when I said, I have a new fiber tract we can test. He told me, what do you need? I told him I have to go and see some cadavers over at ULL because they have a repository of 84 cadavers in the refrigerator. They have facility, an amazing facility for that. And you can get the real tissue from from autopsies. And Ron told me, well, go there for a couple of months and do the job. So that's what I did. And with the local colleagues here, we worked out and we came up with new circuitry for immunity, brain immune interactions. And Zora with Ron were able to pull out a grant, and we pulled out also a paper. So Zora was very kind to say, Nikos, no, it's a very complex collaborative effort, and it starts 10 years ago. Ron Kikini sent me twice in Germany to understand the brainstem in an institution that is just like scientist monks. You close there, you stay there for 6 months in an apartment, and they pay you for that. And you think, this is an amazing experience. And Ron thought of me to do that, and he helped me for this. And I felt creative again after 40 years that I was in science, and I was a busy bee, just doing everyday work and never thinking creatively, really creative. So we could here do something with projects and create a hub between us, just to think about new cool ideas and have the local people to participate, because this, in my opinion, is social work. Social work, to give the opportunity to the local people to do things that they want to do and they think that they should do, but they cannot, because they don't have the technical capabilities, the organization that is needed, and some kind of a model to look at. Okay. One, for example, did his PhD here after he did engineering in Madrid, here in the University of La Laguna with Ernesto Pereda in MEG. Then he went to Texas, and then he came to the Martino Center in Boston, Harvard. But look, and not everybody can do that. There are many, many students here that have to stay here and really work locally. So we are here for this purpose also, to help assist CF Weston. He has the best machine probably of GE on the planet right now. Here they have a GE in the neuroimaging department, a very good 3 Tesla. It's not like CF's, but it's an excellent machine. Do they know to put the protocols they should put for certain research, for post-mortem human, for in vivo human, all these kinds of things? Here is CF that would help them on that. So this is the whole issue of getting together, do cool things together, feel happy about it. And basically the one thing that we also were able to do this year was the workshop for the first time. And we did it in the Canary Islands, where Juan Alzola, organizing the NAMIC, told me before Christmas in a visit I had here, why don't you do it in parallel with the NAMIC? Of course, it was much easier for us because the organization there was already set. It was not only it was easier, it was also very specific for the 3D slicer. It was a workshop they were doing the slicer week, basically, in this. So it worked wonderfully, and I believe that we went one step ahead in all these endeavors, and I would like to thank you all for your participation, even if we don't see many people yet of the local university, but they were more than last year. And you saw that because this year we added 2 morning sessions with their presentations. Unfortunately, they didn't come back for our presentations, but at least they say, we participate. Takes time, it's like a reform of culture. More than that, you know a funny thing? It's a weekend, and they don't come because they are used to just stay home or do their hobbies. Okay, so but probably next year, if we motivate them a little bit more, they may come here, okay, and participate with us also. So look how many universities here. It's organized by ULL, University of La Laguna, and Harvard Medical School, but it's also a participation of University of La Laguna, of Las Palmas, Gran Canaria, where mainly it's Juan Alzola. He has also an appointment here in the astrophysics department, which is an amazing institute. It's a world-class institute. And we take it as a model also to have other institutes here mimic them, understand the mechanism. Then Alto University, the Risto El group that presented yesterday all day for TMS EEG, Florida State University for Development and animal models, and with Pradeep Bide, and Boston University basically for traditional and cutting-edge techniques in neuroanatomy with Jared Rushmore and Doug Rosette. So thank you again for everything, for the support, and we hope to be here next year.